I'd like to start off and say that it is a real honour to be elected a Fellow of the Royal Society Te Aparangi, and it's something that I could never have imagined when I was growing up as a young girl in Aotearoa, New Zealand. In fact, I didn't even know the Royal Society existed back then. I'd like to express my gratitude to those that have supported me throughout my research career, my whānau, my colleagues, my collaborators, and my students. Without them, I wouldn't be where I am today. So thank you all. My talk today is a little bit of a journey through my research career. So I'm going to start off on my own personal journey before I talk a little bit about my research. So as a child, I was inquisitive. I was growing up on an apple orchard in Nelson, or near Nelson, and I'd follow Dad round and he'd have to explain everything he was doing. You know, I'd want to know what's the best way to prune an apple tree, or, you know, how are we grafting these apple trees and why are we grafting these apple trees? It was quite an idyllic lifestyle. So we swam, we played outside, we climbed up and down a cliff. That was a lot of fun. There was a Maori pa nearby on the neighbour's property. So we didn't really have an idea of properties. We just roamed from one to the other. So we spent a bit of time investigating that as well. So it was great, but I knew that there was a whole lot more out there in the world, and I wanted to investigate that. And I think that's what brought me into research. When it came to going to university, I got onto my trusty Honda 90 scooter and rode from Nelson to Palmerston North, taking the ferry on the way. And the degree that I graduated with didn't even exist when I went to university. So that was a Bachelor of Technology in Computer Science. I went on to do a master's degree, and the topic of my master's degree was the design of a monitor for debugging and development of multiprocessor process control systems. So that it was like an IDE for multiprocessor control systems, and it was kind of a sign of the times because multiprocessor systems were brand new then, and the process control system sort of harked back to the machinery on the orchard. So you know, it was very fitting for the life that I'd lived before that. I went on and did a PhD at the University of Melbourne. My research got a lot more abstract at that point. So the title of my PhD there was Theoretical Foundations of Deductive Object-Oriented Databases. So again, this was a sign of the times. It was what was current, what everyone was looking at the time. What I did in that was I used first-order logic to reason over data in a mathematical sense, and also to bring the meaning of the data into the database to help that reasoning. And then we wrote algorithms which matched that reasoning, and we were able to prove them correct mathematically and things like that. So this is kind of the start of this journey that I've got here from data. So I spent quite a lot of time working with data before I moved into machine learning and artificial intelligence. Part of working with data, I carried out a lot of research with co-authors, with collaborators at the National University of Singapore, where we co-authored a book about semi-structured database design. I'm sure all of you don't get quite as excited about data as I do. And we also received a most influential paper award with that group there. So getting on to the machine learning part, many of you probably think that you don't know what machine learning is, but you are using it every day. So examples that you're very familiar with, the first here I've got is predicting COVID cases and hospitalizations. This is something we became very familiar with, regrettably, over the last couple of years. Other uses of machine learning are recommendations of other things that you might want to buy. So when you go onto an online shopping site or you know, it says you might also like to buy blah, or if you're looking at Netflix, you've watched a movie, they say you might also like this movie. So this is all powered by machine learning algorithms. And a further example is the GPS systems, when you're saying that, you know, I want to go home, and it gives you 3 different routes. Again, those recommendations are powered by machine learning. These other examples down here are examples that I'm currently working on. So the first one there is actually a time series example. So time series is quite difficult to analyze using machine learning, and in particular it's difficult to tell when you're going to have turning points in your time series. So when you're at a peak and it's going to start going down. So again, COVID cases is a great example of this, and also when you're at a trough and it's going to go up, so when there's going to be a new wave of COVID. So we're currently coming up with algorithms and testing algorithms to recognise when there are going to be peaks and troughs. Hopefully the second thing there. Another project that I'm working on is describing the risk factors for dementia. So I'm working with a group at the University of Auckland. We have routinely collected data, so it's only small data, and we're trying to get some information out of that about possible risk factors. I'm also doing a small project on predicting the severity of acute pancreatitis, again with some researchers in health. The second to last example here is predicting when a sensor will become faulty. So this is an example out in the environment. You may have sensors in rivers or streams, and you want to know when they're going to need to be recalibrated. So if we've got all the data coming in, we can analyse the inputs from those sensors and judge when we think that those sensors might become faulty, and therefore we can send people out to maintain them when we think they're going to need it. And 2 other projects that we're working on at the moment are predator detection and animal re-identification. So predator detection is obviously useful for conservation projects, and animal re-identification is you may have an image of an animal in one camera, and then you might want to say whether you're seeing the same animal or a different animal in another camera. So again, this can be useful to work out animal movements in the wild and things like that. Okay. So one particular problem that we're looking at the moment is detecting when malicious actors are trying to fool machine learning algorithms. So I thought, rather than try to cover my whole, all the research I'm doing, I thought it'd be useful just to look more deeply into one of the projects. So consider an autonomous vehicle that relies on software. Some of the software will be machine learning models that have been trained on data. So what you might do is train this model on a whole lot of road signs, so that when your car comes up to a road sign, it predicts what that road sign is. So what you'd hope in your autonomous car is that if there's a road sign that looks like that, the autonomous car will recognise it as a stop sign. Okay, so this is some research that's come out of Japan. So what they were doing was looking to see if they could just put stickers on signs to fool the machine learning model. And they had this little moth sticker, and they put it on the sign, and the machine learning model that they were using recognised that sign as a speed limit 80 sign, which could have quite bad consequences. Okay, so how does all of this work? So to start off with, we need to know a little bit about machine learning. So machine learning algorithms build a model based on a sample of data to make predictions or make decisions. I have to speed up. Okay, so if we think about the autonomous vehicle problem, then you might have your sample data is a whole lot of signs and they're all labelled. Okay, we have this other thing called classification. It's a subset of machine learning. With classification, here we've got our labels on our original data set, and we build a model based on that. So we might have pictures like the picture of the panda bear, and the label would be panda. There are these things called adversarial attacks. So adversarial attacks trick classification models into giving an incorrect label. And here we've got an example of an adversarial attack. So we've got a picture of a panda, and a classifier recognises that as a panda. We can add some carefully crafted noise. So this is like some noise, and you overlay that on the panda. And the image still looks like a panda to you and me, but it causes the machine learning algorithm to misclassify it as a gibbon. And what's actually scary is that it was 99% confident that that was a gibbon. Okay, so the research that we have done, so we have these adversarial attacks. People come up with adversarial defences to recognise, if something has been attacked or not. But generally, for every new attack, someone has to come up with a new defence. So what we've done is we've come up with this framework, which we've called BARD, which is blocking adversarial attacks, adversarial examples by testing applicability, reliability, and decidability. So the idea is that you input the image, you input what the label was and the classifier, and it goes through this 3-stage process, and we get a score for each of those stages. That score goes into a logistic regressor, and then based on that score, we can tell whether it's an adversarial example or not an adversarial example. So what we've shown is that this is quite robust, and that it does work across a number of different attacks and classifiers. Okay, so I think my time's up.
That's right, thank you very much.
I'd like to say that I didn't use GPT at all to create the talk.
Wasn't an adversarial attack. So, are there any questions for the speaker, please? Rachel.
Gillian, thanks very much for that. I'm wondering if you can tell us simply, which might not be the case, how on earth the addition of a little moth can change a stop to an 80k? How?
How it does. I guess what happens is that you've got various features that are used to build your model, and if you just change it a little bit, then the features are going to appear different.
But I mean, a moth's not involved in an 80k sign, so the moth is incidental, obviously. It just sort of stuffs makes the computer not follow.
Yep.
Okay,
That's
thanks.
right. Yeah, it's not the moth itself.